Okay, here we are with the recording of the correction of this masterclass by Pablo Piaggi. So Pablo, if you want to share the screen, you can start.
Yes, thank you, Giovanni. Can you see my screen properly?
Yes, I can.
Okay, then. Okay, I'll start with the correction of the exercises. So the idea of the tutorial was to use the environment similarity CV to explore different ways of calculating liquid-solid chemical potential differences. And just a brief recap of the theory. We're using a collective variable based on the density around a given environment. The definition of the density is based on a spreading. This spreading has a parameter sigma that we will determine during the first exercise. The use of that density allows us to define a kernel to measure how similar environments are, and this is given here in this equation. Okay, let's go to the first exercise that is about sodium. That I call it the alanine dipeptide of solids because alanine dipeptide is the standard system to test enhanced sampling methods and to do tutorials, because it's a very simple system. I have tried to choose something that is also relatively simple, and I believe sodium is. I have given some of the reasons here in the description. Okay, so I go to exercise number 1. This is how to choose reference environments for the collective variable and choosing appropriate sigma values in a rational and systematic fashion. Okay, so I'm showing here the input that we're going to use to define the collective variable. We have the crystal structure that in the case of sodium is BCC, and the lattice constants that are appropriate for this model. Okay, so the first thing that we're going to do is a simulation of the liquid and a simulation of the solid, and that's shown here in this Jupyter notebook that is already uploaded to GitHub. So we do a simulation of the solid. It looks like this. And we do a simulation of the liquid. Looks like this. Okay, now that we have these simulations, we calculate the distributions of the kernel. So here we're comparing the reference BCC environment with the environments that exist in the simulation box. And what we're going to do is calculate these distributions. This is done as shown here in the instructions. It's done with this PLUMED input that calculates a histogram with the input being the kernel calculated by the environment similarity action. And then we're printing the grid with the histogram to this file histo. We're repeating this calculation for different values of sigma, and this is what I will show here in these plots. So here we have the distributions of the kernel for the liquid and the solid. The liquid is shown in orange and the solid is shown in blue, for different sigma values from 0.01 nanometers to 0.12 nanometers. What we see is that as we change sigma, we go from distributions that have a lot of overlap, and what this is, I mean, the physical reason why we're seeing this is that we're being too strict with the comparison of environments, and therefore we're finding that none of the environments are actually BCC because they have thermal fluctuations. As one increases the sigma, making the definition more lenient, we see that we have better separated distributions, but eventually as this sigma value becomes too large, it's like comparing anything with anything, and also we start having issues of overlap. But in between, there is a sweet spot around 0.07, I would say, where the distributions are well separated, so we're able to distinguish very well between the two phases that we're studying here, the liquid and the solid. Okay, a more systematic way to think about the choice of sigma is by calculating the overlap between the distributions of the liquid and the solid, or in general of two phases. And the measure of the overlap that I will use is this one, so the integral over the minimum of the distributions. And if we do this calculation for different values of sigma, we can obtain this plot that I'm showing here, that is also calculated from the distributions that we computed before. I gave a script last week to be able to compute this, but it's done here also in the solution of the exercise. Okay, so here I'm plotting overlap versus sigma, and you can clearly see that there's a minimum. If we zoom in this region, here we see the minimum even better. So the best choice of sigma for the collective variable is this one. I mean, it is the one that will distinguish best between the structures that we're considering. An important thing that I would like to highlight is that actually many of the values that we have here would work relatively well and would be good choices, but of course we can choose the best, which is the minimum. Okay, so now that we know that 0.07 nanometers is the best value for our parameter sigma, that is essentially the only parameter that we have to choose for the collective variable.
Sorry, Pablo,
yes.
can I ask a question?
Sure.
So about this, so quantitatively, how can one interpret this number? So does it mean that one atom every 20 will be misassigned, more or less?
I'm not sure it's from the overlap you can say that. Certainly you can say that based on the distributions, in the sense that you know the exact fraction of atoms that are mislabeled.
Okay, so if you compute that fraction, that would tell you how many of them are mislabeled.
Yes, yes. So you would have to compute the tail of the distribution, say beyond the threshold that you choose.
Yeah, clear.
Yes. Anyway, so within this framework, I mean, we're doing the best that I think that it's that one can do, having relatively small environments. I mean, you could do other things not to improve the discrimination between the phases, but it's probably going to be more expensive, like choosing larger environments. I didn't include it here, but I actually did test that larger environments, of course, lead to better discrimination.
I see. Thanks.
Thanks for the question. Okay. So once that we know what's the best parameter that we can choose, what I'm showing here is the distributions of using this sigma value. And what I'm doing here is identifying the threshold at which both probability distributions have the same value, which is connected to your question, Giovanni, regarding the mislabeling. So it's a way to choose the threshold such that the mislabeling is similar between the two phases. And we're also identifying the position of the maxima of the distributions. Okay, so that's it regarding the setup for the collective variable. Once that is done, one can start doing the actual calculations. So we know that we have chosen good parameters for this. So now I'll move to the methods to calculate liquid-solid chemical potentials. Of course, I'm focusing on different ways in which you can do this using enhanced sampling. There are other ways to do it, but I think in the context of the tutorial, it is interesting to see the different ways that one can use PLUMED to calculate liquid-solid chemical potentials. Okay, so I'll go here to the to the exercises on the PLUMED manual. So the idea of this method is actually quite simple. So we will try to convert the liquid into the solid reversibly. Once that we have that simulation, the equation that I'm showing here on the screen is a simple way to calculate the difference in chemical potential. We have here the partition functions of a phase alpha and a phase beta, and I'm showing here the definition of these partition functions. And we will use the environment similarity kernels that we defined before in order to construct a collective variable and choose a threshold such that we can identify properly both phases and also drive the transformation of one phase into the other one. Of course, in a standard MD simulation, you wouldn't observe any transitions, so we must introduce a bias potential in order to see the transitions. Here I chose to use OPES. One can also use metadynamics or any other method. I just chose this because I thought it was a simple way to go about it. So what we will do is the following. So we define the collective variable as before using the sigma value that we determined before. And now, since this is a per atom quantity, we will define some global variables. One is the mean of these of the kernels, and the other one is more than that you're seeing here. And that means that we're counting how many molecules have or atoms have a value of the kernel larger than something. Here we have to choose some switching function. We're using a switching function that is 0 up to 0.38, then goes up to 0.8, and then stays at 1 at 0.8. The rationale behind those numbers is what we have seen here. So essentially, we have a switching function that is 0 up to here, then goes up, and then goes to 1 in this region. And in that way, we're counting the number of solid-like atoms. Okay. So now that we have a collective variable that represents the number of solid-like atoms, we introduce a bias potential using that as the collective variable. We're going to do this for different temperatures. And I think I have some. Okay, so first, let's see what's the behavior of the collective variable. So the number of solid-like atoms as a function of time for different temperatures. We see that there are many fast and reversible transitions between what would represent the solid, that is the region at very high CV values, and the liquid, that is around 0 solid-like atoms. We see very nice and fast reversible behavior for all temperatures. Of course, it's nice to visualize the trajectory and see what's going on. So let's do that for the system of 250 atoms. That is the one that I suggested to study in the tutorial. So there you see we have the atoms moving around in the liquid as usual, and then they form the solid. That's the BCC solid. And then we see the formation of the liquid again. I'll do it again. So that's the solid. And that's the liquid that we had initially. So this is happening many, many times during the simulation. So this is a relatively long simulation of 100 nanoseconds. We have, well, many, many transitions in this time frame. So it's very easy to calculate the difference in chemical potential when one has so many transitions. We can also do the same for a system with 1024 atoms. There we see a similar behavior. So eventually, yes, there we form the solid, and then we'll form the liquid again. This is just an excerpt of the total trajectory. I chose it such that one can see one transition clearly, because otherwise it would be hard to pinpoint the transitions having so many. Okay, so once that we have these very nice simulations, we can analyze them. Perhaps the most straightforward thing to do is to calculate the free energy surfaces. as a function of the collective variable that we used for biasing. This is what I'm showing here. So we have free energy in kilojoules per mole versus a number of solid-like atoms at different temperatures. And what you can see is that we have at all temperatures two basins, but they shift in stability as one changes the temperature. Initially at 360, we have that the solid is more stable. And as we go to higher temperatures, of course, the liquid becomes more stable. And eventually at 420 Kelvin, we're close to the limit of metastability, in the sense that the solid is, it's not beyond that temperature. It's not going to have a minimum in free energy anymore. So it's approaching the limit of metastability. Okay, so that was one of the things that that I proposed to do. So I asked, what is happening during the simulation? And well, we're seeing reversible transitions between the liquid and the solid. Are there transitions? Yes, many. Another interesting thing is that we have the solid well aligned with the simulation box. That is something that I had asked here. And this is because the collective variable is non-rotational invariant. So it's forcing a particular orientation of the solid in the simulation box. And this is, of course, very useful because it essentially guarantees that we have no defects and no strains. No stresses in the simulation box. The free energy surfaces that we just computed and I just showed are calculated in this fashion as usual. So it's just so the free energy is -1 over the inverse temperature logarithm of the probability distribution. We're calculating this probability distribution as a weighted histogram, and it's very easy. You can see it here. It's just a NumPy histogram call using weights that are given by the bias potential. Okay, so the next task is to calculate the actual chemical potentials. And this is calculated as I showed initially. So I'll put the equation in the screen again using this equation. And the partition functions are just a sum over the weights that we have in the simulation, restricted to each phase. That is also very, very easy to code. And here I'm showing an example of a function called free energy that, given some threshold called here CV limit, it's calculating the ratio of these partition functions. So in other words, we're comparing the probability of finding the system in the liquid phase and the probability of finding the system in the solid phase. That's also very easy. Okay, now that we have this function, we use it to calculate the chemical potential. I'm doing this both for a system with 250 atoms and a system with 1,024 atoms. I calculate the chemical potential for both. And what I'm showing here on the screen on this plot is the chemical potential difference as a function of temperature for both these system sizes. We see very, very strong finite size effects. If you have experience with this kind of a simulation, you will be familiar with these very, very strong finite size effects. So given that we have two system sizes, we can also extrapolate to the thermodynamic limit, and that's where we are going to do next. So what we plot here is the chemical potential difference as a function of 1 over system size. We can nicely extrapolate to the thermodynamic limit. I guess one could compute an extra chemical potential for a different system size to have 3 points. But this works well. I mean, I have done it for other systems. So in this case, 2 system sizes is enough and works well. Okay, so now, here the points that we have in the were these lines that we're using for the extrapolation, where they cross the y-axis. These are the chemical potentials in the thermodynamic limit. So we can plot also these values, and this is what I'm doing. So here we have the chemical potential difference as a function of temperature for the two system sizes that we studied, plus the thermodynamic limit. And we can calculate the melting temperature or the coexistent temperature if we're considering two phases in general. And what we get is a melting temperature of 366 Kelvin. That is the one reported by the authors of the potential that we're using. So this is working well. I'll do a comparison with other methods also afterwards. Okay. Let me go back to the questions I raised in the tutorial. Yes, whether one finds the same chemical potentials and coexistence temperature for different system sizes. Of course, the answer is no. The finite size effects are huge. One must be super careful with that. But well, we know how to handle them. We have to be careful. By taking this into account, we get a very good coexistence temperature. So the error is around 1 Kelvin or perhaps below. And then the last question is, which system size or which system sizes are big enough to make an error of about 1 Kelvin in the coexistence temperature? That's also easy to do. So we plot the coexistence temperature versus 1/n. And I would say that a system size of around 2,000 atoms would give an error in the melting temperature of around 1 Kelvin. So it's relatively large, but this of course depends on the properties of the system, on the heat capacities, on the enthalpies. So sodium is particularly hard, I mean, in the sense that it has a large finite size effects. Okay, so that's it for exercise number 2. That was the bulk interconversion method. It's a name I coined myself. I'm not sure if someone has given it a different name in the past. Okay, so now that we have gone through the resolution of exercise number 2, we can go to exercise number 3, the biased coexistence method. This is also a name I invented myself, but this method is based on the following strategy. So one considers the one phase in direct coexistence with the other phase that we're interested in. In the case of this exercise, is a liquid in coexistence with a solid. So there was I would say a relatively well-known method is the interface spinning method, and the idea here is to put a harmonic bias potential such that the number of solid-like and liquid-like atoms fluctuates around a given value. That is to say, the system will not be able to melt or to grow due to the introduction of this bias potential. So I call it instead a biased coexistence, because I think when one uses more sophisticated methods for sampling, we're not pinning the interface, but rather we're controlling in the way that we want how the system grows or melts. What we will do here is we will restrain the region in which the system is able to grow or dissolve to one layer of the crystal, and then we're going to add a bias potential such that this interval, so the growth and dissolution of one layer, is sampled efficiently. So, well, before going into the details of the PLUMED input, the idea behind the method is that the chemical potential, just heuristically, without doing any proof, is proportional to the number of well, for instance, the solid-like molecules. This is also, I mean, the definition of chemical potential. There are some caveats. We have an interface. There are many things. One has to choose also. I mean, by choosing another parameter, one is choosing what's called the dividing surface, and also that will affect the thermodynamics. But heuristically, the idea is that the slope of the free energy with respect to the number of molecules is going to be the chemical potential. That's the core idea of the method. Okay, so we'll do a simulation of the two phases in direct coexistence. Here we will use a larger system size, 2048. Here we can use a larger system size because we're not going to crystallize and melt the whole system, but rather we're going to study a small interval in the say in the growth or dissolution process. So we can study larger systems relatively easily, which is an advantage of this method. Okay, so what we're going to do is the following. So the plumed input is we will have an upper wall and a lower wall that will limit the growth or growth or melting of the system. We choose values that are consistent with making just one layer grow or dissolve, one layer of our crystal. Once that that we have that, we can add a bias potential. Here also we're using OPES. And we're going to sample reversibly this small interval of growth and melting. Okay, so let's see how the simulations look like. So what I'm showing here is the behavior of the number of solid-like atoms, so our collective variable, as a function of time for different temperatures. You can clearly see that the interval that we're targeting is sampled nicely. So once that we have this type of simulation and a lot of statistics, we can do very rich analysis. But before going into that, I would like to show how the simulation box looks like. So this is the system that we have. So we have on the left here the solid, and on the right the liquid. And what we're going to see is a very subtle, maybe not you cannot perceive it here, the growth and melting of a layer, because the interface also looks diffuse, not from in this way. Okay, so this is the system, and this is what we're observing. Here, of course, the transitions are not as clear as in the previous method, but we will be able to get very robust results, as you will see. Okay, so we have these simulations, and the analysis that we're going to do is we're going to calculate the free energy surface. So here I'm missing the axis. So this is free energy in kilojoules per mole, and this is our collective variable, so the number of solid-like atoms at different temperatures. What you see is that as the temperature changes, we're seeing a change in slope. And now the free energy looks very linear, which is, I mean, it's convenient in this context, but it's also a reflection that of the growth and melting mechanism that is rough growth, that is molecules attach in whatever way they want. Now in more complex systems, we would have some feature in this free energy surface that might represent, for instance, that the system has to, in order to grow a layer, has to overcome a free energy barrier. In that case, I argue that if one samples a very small region of the number of solid-like atoms, you would likely make a mistake, because the slope that you would calculate from these plots is affected by that. In that case, sampling one or more the growth of one or more layers averages out the effect of the growth mechanism. So it's also an effective way to study the to calculate the chemical potentials. But in this case, it's a model system, and this works very well. So now we calculate the slopes of these free energy surfaces. We can plot the slope, that is the chemical potential difference, as a function of temperature. We get also a very nice linear behavior. And from the intercept with the x-axis, we get the coexistence or melting temperature. Then in this case is 376.3. It's a bit higher than what we found before in the thermodynamic limit, but it's also consistent with the finite size effects that we expect for this system size. Anyway, I would say most methods have an accuracy of around 1 Kelvin, unless you do special things. For instance, if you're doing direct coexistence, you need to consider huge systems in order to get a small error in the determination of the melting temperature. Okay. Let's see if I had any other questions in the tutorial. So are the free energy surfaces linear with the number of solid-like atoms? Yes, in this particular case. We find a melting temperature that is in relatively good agreement with what we were expecting, but slightly larger. That it's also in agreement with the behavior of finite size effects. Okay, I wrote here also discuss the advantages and disadvantages of the two methods presented above. I leave that as an exercise because I think it's to some extent it is could be subjective, and I don't want to introduce a bias into other people's opinion. Okay, and so we can move, I think, to the last exercise. So this one does not involve Plume, but it's a very easy and well-established method, and I decided to include it here as a reference. Thermodynamic integration is it's a very general method, but this one in particular is the thermodynamic integration along isobars, and it's based on the following equation. The idea is that if we know the difference in chemical potential for some thermodynamic condition, we will be able to compute it at a different thermodynamic condition just by integrating the difference in enthalpy between the phases divided by the temperature squared. This is, of course, very easy because the enthalpy is a quantity that is very simple to compute. We don't need any specialized methods to do that. Of course, the caveat here is that you need to know the answer of at least for at least one thermodynamic point before starting. That can be easy or hard. It depends on the problem at hand. But it's, of course, a very nice way to check for the consistency of results, and also it's very cheap. So if you do know the answer for one thermodynamic condition, it might be best to just do this. That is straightforward. Okay, so I gave the scripts to calculate to do the simulations of the liquid and the simulations of the solid, and calculate the enthalpies for each phase at different temperatures. So let's see what we get from that.
Sorry, Pablo, a question on this. So in the end, even though it looks straightforward, you have to compute the energy for each frame and then compute its average, and then this might have very large errors, right?
The enthalpy.
Yeah.
You're thinking that it might have a large error because you have the integral, so you're summing over the errors that you get at each thermodynamic point.
Yeah, so they will sum up, and then for each point you run a simulation and you compute this delta H.
Yes.
From a finite number of snapshots, right?
Yes, but I mean, this is typically very fast, no, compared to the simulations that we considered before. So imagine now that this potential can do something like 1,000 nanoseconds per day. Well, of course, it depends on the system size and the number of processors, but in general, that's the number. And the with Plume, then the overhead of calculating the collective variable, we get maybe more like 100 or even less. So I would say, I think unless you're in a condition where the enthalpy is particularly hard to compute, say that you are close to I mean, to the Widom line in water or something like that, where the fluctuations explode. Well, not really explode. I mean, at the critical point, they would explode. I mean, if the Widom line, they would be very large. It might be hard not to.
I see. Maybe I'm confused because in the case of biomolecules, typically you have like small differences which are dominated by large fluctuations in the solvent, whereas here actually you are taking the total enthalpy.
Right. Yeah.
So and then you divide by the number, so you get that specific energy.
Yes.
So in the end, these fluctuations are low, are very low.
Yes. It's. I think it's typically very easy to do simulations long enough such that the difference in enthalpy, I mean, the error in the enthalpy is small.
I see.
Yes, it's this works well, but of course you might. Yes, you can control the errors, but of course you have one point that is known, and if there's an error there, it will certainly propagate throughout all of your calculation. Instead, in the methods that we saw before, each point is completely independent. So it might be a good strategy, say, to calculate a couple of points using the other methods, and then if you want a finer resolution, you can use something like this. That might be a good strategy. Yes.
I see. Thank you.
Thanks to you.
And then maybe another comment. This looks a bit more like umbrella sampling. So you follow. This looks a bit like umbrella sampling, where you set up multiple simulations in between, but you don't necessarily have transitions.
Yes, you don't have transitions at all.
Yeah, so maybe it's safe for these systems where it's easy to monitor what's the state of each particle.
Yes.
But if it's more complicated, then you might have like hysteresis effects or so.
In my opinion, yes. I mean, of course, doing something like this that is less physical because you don't have real transitions. I mean, the actual physical phenomenon is not happening, has risks. For instance, say that these are subtle things, not, but for instance, if you consider the case of ice, where you have a proton disorder, here you would start from some particular proton disorder, and you would assume that that stays constant throughout the calculation, which is not true. So you're introducing, I mean, by doing something that is, I think, non-physical, you introduce potential errors. Now, everything that is physical, it's harder. So I think there's a trade-off between the two approaches. I think that's my point of view.
Yeah, you can make the problem simpler, arriving easily to the wrong answer.
Exactly. Which you could argue the same for umbrella sampling, I guess. If you're not careful, of course.
Yeah. Okay. Thank you.
Thanks for the question again. Okay, so let's see the solution to the exercise. So we do very simple MD simulations, which we calculate the enthalpy at each for each frame, and then what I'm doing here is I'm computing the mean of the enthalpy. We have the output, the thermodynamic output, in this file thermo.txt, and here column 1 is the enthalpy. Okay, so here I'm showing the enthalpy as a function of temperature. Of course, the blue curve that is lower in enthalpy corresponds to the solid, and the curve in orange corresponds to the liquid. Here we see that at 420, I'm not showing the results because we're so close to the limit of metastability that the system spontaneously transitions to the liquid phase. Okay, so now that we have this enthalpy, we can of course calculate the difference in enthalpy as a function of temperature. We can fit a spline to that, and then we do the integration. Here I'm just using the the trapezoid rule to do the integration. And in that way, we get the chemical potentials as a function of temperature. Here, what we're assuming is that the melting temperature is 366. So of course, here, if we're propagating an error, we should bear in mind that this determination of the melting temperature will also have an error bar, and it has to be propagated accordingly. So in other words, it's likely that we will get a systematic shift of all the chemical potentials because of the assumption of that particular state point. This is also not true for the other methods because all points are independent. Okay, so this is the chemical potential difference as a function of temperature. I think that's the resolution of the last exercise. So the only thing that we're left with is comparing methods and perhaps discussing them. So now let's put together the chemical potentials that we have calculated using all methods. It's just a simple plot with all three methods. Here I'm not showing error bars, which of course, if this if this is it's going to be a publication, we should put the error bars. So I'm showing in blue the biased coexistence method. So this the one in which you have the two phases at coexistence. This is shown in blue. We have the bulk interconversion method with the extrapolation to the thermodynamic limit. That's shown in orange. And we have the last method that we use, thermodynamic integration, that is shown in green. What we see here is that methods agree best close to coexistence. And the reason behind this, you see more systematic errors if you go to the farther from the coexistence temperature. And this is showing one of the weaknesses of the biased coexistence method, that is that it depends a bit on the order parameter. So here, the one that we chose the analysis depends on the order parameter besides the actual biasing. So the one that we chose is producing a small artifact. If we chose a different order parameter, we will get a slightly different results. So here you see that at high temperatures, the chemical potentials seem consistently overestimated, and at low temperatures consistently underestimated with respect to, say, thermodynamic integration. If we compare thermodynamic integration with bulk interconversion, we see that they have also a systematic shift. And assuming that the extrapolation to the thermodynamic limit has been done properly, the conclusion of this would be that thermodynamic integration does have a systematic shift caused by the fact that we're making an assumption on the initial state point, that is the coexistence temperature. And in general, I would say it depends on the accuracy that you're targeting. Of course, the agreement between methods is relatively good. They have each of them has systematic errors. I said that I was not going to introduce a bias in other people's opinion based on my subjective experience. So, those are the results. You can judge for yourself what works best. The last thing that I would like to mention, that is also mentioned in the tutorial, is that one method that I'm not discussing here is Hamiltonian thermodynamic integration. For instance, the Frenkel-Ladd approach based on the using as reference the Einstein crystal. I'm not discussing that because it's not based on enhanced sampling using Plume, and this is a tutorial on that. But it's also a widely used technique. And I think more importantly, typically the tools that I described now are complemented by the integration of the Clapeyron equation. This technique was pioneered by Kofke, and he calls it Gibbs-Dachem integration, but it's based on the integration of the Clausius-Clapeyron equation. And I'm mentioning this because in the same way that given us 1 point, we can compute the chemical potentials with thermodynamic integration along isobars. Given a coexistence point, we can obtain a whole coexistence lines using the integration of the Clausius-Clapeyron equation. And this is very important in the context of the calculation of phase diagrams. And I thought that doing a tutorial without mentioning the importance of that technique would be a mistake. So at least I'm mentioning that that's something important in one's toolbox. That's it. We got to the end of it.
Yeah, thanks a lot, Pablo. It was very clear. And yeah, so thanks again for sharing your experience and for trying not to bias people in our community with your personal